First problem I want to work through today is to figure out the volume of a pyramid based on having a square base with lengths 2 meters and 2 meters. And let's have the height be 2 meters as well. This is an example from the book. It's an exercise. The volume of such a pyramid can be found without using integrals. The volume ends up being 1/3 the volume of the corresponding box that this would sit in. If you could pack it in a box tightly with 2-meter sides on the base of the box and a height of 2 meters, the volume of such a box would be 2 times 2 times 2, 2 cubed, or 8. The volume of this is going to be 8/3 cubic meters, about 2.67 cubic meters is going to be the answer. But let's derive that with calculus because that gives us the skills that we want in attacking problems like this, whether they be geometric problems that are just giving us pure areas or pure volumes or pure lengths, or more physics-oriented problems like we will do fairly shortly after spring break, involving figuring out the work done by a force and things like that. Doing geometric problems is also useful in a class called mechanics, which is not about fixing your car. It's about understanding the motion, whether it be simple motion of particles or more complicated motion of objects like flying through the air and twirling as they go, like a baseball bat flying through the air. That's more complicated. You need these kinds of skills to be able to analyze that kind of motion well. You don't have to do this, but I will do it anyway. I'm going to draw in a vertical axis here with the origin at the midpoint of the square there, going up through the top of the pyramid. And since it's a vertical axis, I'll call it Y. And we want to find the volume by slicing. You use an imaginary knife in your mind, or literally maybe with your hand. Slice this, but how? We could slice it lots of different ways. I mean, you could slice it with vertical slices like this, or even slanted slices like that. Well, it's going to be simplest to slice it with horizontal slices. The reason that's probably simplest is because when you slice it with horizontal slices, the thin pieces of bread, you might say, that you get, if you imagine this is a loaf of bread, would be shaped like squares effectively, though the sides would be a bit slanted as a 3-dimensional object, a box with slanted sides. That's okay, though, we'll see. So you can draw in a typical looking slice in here if you want. Typical looking thin slice of width or height for the slice. Oh, how about call it delta Y like we've been doing? We want to think of this as a small number. We will also think about the infinitesimal version of this because that's something that's done in many science textbooks. So I want to get you used to it. And it is kind of a nice way to think about it, which really avoids thinking about Riemann sums. So it's nice in that way as well. So I might also think of this as an infinitesimal height and label it with a dy instead of a delta y, but let's initially do it the Riemann sum way. Label it delta y. What is the small volume of that thin slice? Call it delta v, small volume of thin slice. I add the word small in here just to emphasize that's the way you're intuitively thinking about it. We're thinking about the slices being really thin and trying to find that small volume. Because it's so thin, it will be a small volume. Pretend the sides are not slanted. Pretend they're vertical. These thin sides in the slice here, they are slanted. I mean, it comes from a pyramid. But as those slices get smaller and smaller, the amount of volume that the slanting contributes, you might say, gets smaller and smaller as well. So in the end, it's like you can ignore the slanting and think of them as vertical, and think of this as being approximated as the product of a cross-sectional area times that small height, delta y. A of y is the so-called cross-sectional area of the thin slice. If you were looking straight down at the slice, imagine you're up here, looking straight down, it would look like a square. So that cross-sectional area would be the area of a square. Let me call the side lengths of the square L for length. Make a cursive L. And those things, those lengths do depend on how high you are. They depend on y. Imagine effectively the y coordinate, the second coordinate of this thin slice as being, well, let's just simply label it y. I'm abusing notation. I'm using the same letter y for both the axis label and that height. I'm also not really worried about whether it's at the bottom of the thin slice or at the top of it or at the midpoint. It doesn't really matter. I mean, it would matter based on which numerical integration tech you decided to use if you wanted to use numerical integration. But for our purposes of just trying to set up the integral, it doesn't matter. We can be kind of sloppy here. Initially, the book's not so sloppy. They label it y sub I, but then they sort of say, hey, we're tired of all these subscripts. Let's not bother. And that's where we are right now. So L depends on what y is. You can see it in the picture. The bigger y is, the smaller L is going to be. This distance right there, that's L. It's a function of y. L of y. And A of y, being the area of a square, is going to be the side length squared. L of y squared. I still got to figure out what L of y is. I haven't done that. I got to figure out what it is. But let's save that. What's the infinitesimal version of this? Infinitesimal version of this approximate equation. What do? You change all the deltas to d's, and you change the approximately equal to become an exactly equal to. dv equals a of y dy, which you could think of as L of y squared dy. That's the infinitesimal version of this approximate equation. What's going on here? I've emphasized this a lot. This is, you might say, fake math, right? Pretend math, a convenient fiction, at least in the standard approach to things. There is actually a subject, a math subject, which is rigorous math, called non-standard analysis, that involves things called hyperreal numbers, which are beyond your imagination. I don't even want to go into them at all, where you can make all this infinitesimal stuff rigorous. But I picked up a hyper-real numbers book off the shelf, non-standard analysis. I looked at the first page and I put it back, okay? I didn't feel like studying it. I mean, I could have, I just didn't feel like it. I had other things to do. We're fine with an intuitive approach to it. We're not trying to prove anything. We're just trying to derive equations. So we're happy with an intuitive conceptual approach, but just realize it's not rigorous math. The main downside of the approach when you do it this way is, like, with more complicated problems, you might feel like, am I really doing this right? But that's kind of similar to what happens with Riemann sums as well. You still have the same kind of feeling. Am I really doing this right? It comes from experience to sort of at some point you're like, oh yeah, I am doing this right. I've done this kind of problem before. It makes sense. That's where you want to get to. I haven't written down a Riemann sum yet. Let's do that next. The total volume, V, you could say equals the sum of the little volumes. I could write summation of the delta V's without bothering to write I goes from 1 to n, without bothering to write a subscript of an I there. I mean, I could, just feeling like being lazy here, because we're just trying to get to the integral, trying to understand the concept. Summation of a of y times delta y. Oh, and this is an approximately equal to here, which we could write as a summation of L of y squared times delta y. And then in this Riemann sum approach, we take this and we say, let delta y go to 0. Take a limit effectively as delta y goes to 0. Back in chapter 5, when we defined definite integrals, we said they were limits of Riemann sums as n went to infinity. N was the number of rectangles. If all those rectangles, again, have the same width, delta xa, letting n go to infinity is the same as letting delta x go to 0. That's effectively what we're doing here. And in the limit as delta y goes to 0, the Riemann sum becomes an integral, which I could write like this, or ultimately like this. I can write it either way for this example. However, if this is going to be useful, it has to be a definite integral. It has to have limits of integration. I can't do anything if I don't have any limits of integration here. I mean, I could find an antiderivative, but that's not what I'm trying to do. I'm trying to find the exact volume of this thing. So I need to go back to my picture and say, how does y vary? Y varies between 0 and 2, because the height of the pyramid is 2. Y goes from 0 to 2. So I need a definite integral. So I do that. Effectively, you could think of this as a definition of the definite integral. It's nothing magical going on here. Technically, that's not quite right, because technically, if you're in an advanced real analysis class, your Riemann sum definition of the integral is much more subtle than what we've hinted at. And then technically, this is a theorem instead of a definition. You got to prove that this gives you the same value of the integral. But it will when your function is nice. With the infinitesimal approach, you don't bother writing a summation sign in the usual sense, at least. You write a summation sign in the conceptual equation version. The total volume is the sum of the little volumes, where the integral sign here in this conceptual convenient fiction approach, you're imagining to be a sum. A conceptual thing, you're imagining it. The total volume is the sum of the little volumes. If you add up all the infinitesimal contributions to the volume, somehow you get the total volume. But those infinitesimals, right, they're really tiny. They're way smaller than 10 to the negative 100 power. I mean, that summation is, it's not literal. It's a convenient fiction. Then you also do want to replace dv with what it equals. A of y dy in general. In our example, that's the same as L of y squared dy, because our cross-section is a square. That's why it's the same. And you ultimately end up with the same formula anyway. And then that's the thing you have to compute. So all this is set up so far. But how do we actually do the integral? We need to figure out what L of y is. That's usually the harder part, actually, to tell you the truth. Use the picture somehow to figure out what L of y is. I hope it seems intuitive that it should be a linear function of y that equals 2 when y is 0 and 0 when y is 2. L of y should have a graph that goes from 2 down to 0 as y goes from 0 to 2. Slope of -1, the formula for L of y should be 2 minus y. That should be right. Should seem right, at least, because the sides of the pyramid are straight. Should seem like L of y is a linear function of y. Is there some other way to confirm this? We want to be a little extra sure of our answer here. We could go back up to this picture and maybe draw in a right triangle here. And notice that this side of this triangle has length L of y over 2. This side has length 2. I want to figure out this length right there of a sub-triangle of the bigger triangle that's similar to the bigger triangle with the same angles. Let me redraw that down here. There's the big triangle, big right triangle. This is L of y divided by 2. This side here is 2 meters. I'm at an arbitrary value of y. The other triangle that's similar to the original triangle is this one right here. It's got the same angles. It's a smaller triangle. Oh, I made a mistake. This is 2 divided by 2 here. This is 1. This is L of y over 2. This length right there is 1. Can I use facts about similar triangles to find L of y? These two triangles being similar means ratios of corresponding sides are the same. So the ratio 1 divided by 2, for example, this length here divided by this length here should be the same as the ratio L of y over 2 divided by this length. That length right there is 2 minus y. You could also use the fact that this is evidently a 64, 30, 90, 30, 60, 90 degree triangle, I think, as well. Anyway, 1/2 will be the same as L of y over 2 divided by 2 minus y. Multiply both sides by 2 minus y. You'll get 2 minus y over 2 equals L of y over 2. Multiply both sides by 2, you get L of y equals 2 minus y, just like I guessed. It worked. Go back up here now, do the integral. Integrate from 0 to 2 minus y squared dy. Couple different ways you could do this integral. You could expand it. FOIL, 2 squared is 4. Outside and inside products become minus 4y and then plus y squared. You get 4y minus 2y squared plus 1/3 y cubed evaluated from 0 to 2, which gives you 8 minus 8 plus 8/3, all minus 0. The 8's cancel, leaving you with 8/3. Just like I said, the answer would be way back at the beginning, right? 8/3 cubic meters. 1/3 times 2 cubed. You also could do this integral actually without expanding it. You could realize an antiderivative is negative 2 minus y cubed over 3. You also could let w equal 2 minus y if you like. dw would be negative dy. That's a 2 minus y right there. Any way you do it, you're still going to get the same answer, 8/3. Number of things going on here. Part of it is setting things up. Once again, I want you to be able to do it with the Riemann sum approach like this, and also the infinitesimal version. But then you want to go from those things to the integral, and you'll get the same integral either way. Then you have to do the integral, which also means you need to figure out what a of y is in general. And for this example, because the cross sections were squares, that's the same as L of y squared. If they were not squares, but they were like circles, then a of y would be something else. Pi times maybe r of y squared, where r is a radius of a circle, a cross-sectional circle. What a of y is depends on the shape of the cross section.